Hello, in this talk, I will present our work DWAY. This work was done at the University of Edinburgh in collaboration with the University of Utah and is supported by an ARM PhD fellowship program. DWAY is a unique design point in the DRAM reliability design space. It provides three key benefits. Firstly, DWAY guarantees improved DRAM reliability. Second, it provides memory performance gains. And thirdly, the ability to avail higher on-demand reliability. We will now delve into how DWAY achieves each of these in detail. Let's start by taking a look at how DWAY provides its reliability benefits. The motivation behind DWAY is a need for increased DRAM reliability. In the real world, we see that growing DRAM error rates are a constant cause of concern, as seen in these numerous press reports. Several field studies have then characterized these errors and observed the increasing variety and granularity of DRAM errors. The inverted pyramid here represents the increasing data that is lost if errors occur at that level. DRAM reliability mechanisms over the years have been incrementally adding new mitigation techniques to protect against errors rising up in the memory hierarchy. Starting with SegDead ECC and row column sparing to detect and correct cell and array level errors, to chip-kill ECC to handle DRAM chip level errors, all the way to IBM RAM and Intel memory mirroring techniques to handle channel level failures. However, all these error mitigation techniques are gradually adding performance overheads because they introduce additional checks in the critical path. DWAY brings the insight that having full replicas and not just the ECC code, and secondly, keeping these replicas as far apart and disjoint as possible allows tolerating errors arising from anywhere in the memory path. Now let's see this in an example. In a conventional multi-socket system, each socket has a DRAM memory array co-located with it, and the sockets are connected by a point-to-point cache coherent link. In our example, socket 1's memory array holds cache lines X, Y, and Z, and socket 2's memory array holds cache lines A, B, and C. DWAY replicates the data present in each socket's array into another socket's memory array. Applying DWAY's replication to our example here, both socket 1 and 2 now hold all the cache lines in the system in their respective local memory arrays. For detection, DWAY can use existing detection mechanisms like ECC, CRC, parity, or employ even stronger detection-only codes. It can also use other diagnostic capabilities like temperature sensors to mark failed components and simply rely on the replica for correction. Thus, DWAY can robustly handle a wide variety of errors arising from faults in any of the DRAM components, from cells all the way to even memory controllers. We quantify the exact reliability benefits of DWAY by analytically modeling a system with a uniform DRAM device fit rate of 66.1. The fit rate is the number of failures that can be expected in 1 billion device hours of operation. The fit rate is a standard metric to define failure rates, and the rate that we use here is derived from Sridharan et al.'s field study report. We calculate the detected but uncorrected error rate, DUE, and the silent data corruption error rate, SDC, of the entire system with different configurations as the figure of merit. Note here that DWAY can work with any detection capability. Thus, we equip DWAY with a detection scheme having the same capacity overhead as the scheme being compared against, and this ensures a fair comparison. We compare DWAY against three reliability schemes: chip-kill ECC, which employs an ECC code which guarantees recovery from one DRAM chip failure in a rank; IBM RAM, which adds redundancy across 5 gang channels; and Intel memory mirroring technique, which replicates data on 2 channels of a single memory controller. Both IBM RAM and Intel memory mirroring guarantee recovery from one channel failure. Let's look at some of the key results from the analytical model. Compared to chip-kill, DWAY provides a 4x reduction in DUE rate. DWAY also provides a significant reduction in SDC rate over chip-kill, as DWAY can use the extra capacity that is obtained by relinquishing the correction code to store a strong detection-only code. Compared to IBM RAM, DWAY reduces DUE by over 2 orders of magnitude. DWAY has a slightly higher SDC, since the total number of DIMMs in DWE is higher because of full replication. However, the SDC rate is already in the order of 10 power minus 10, making this increase negligible. In comparison to Intel memory mirroring, DWE factors in temperature gradient effects on reliability and can map data in a thermal risk-aware manner between the replicas. Thereby, it is able to reduce DOE by 11% over Intel memory mirroring. The full details of this model are available in the paper. An intuitive way of understanding these results is that ECC and RAM are a K out of N model systems. That is, they rely on N minus K out of the N parallel hardware entities to operate correctly. In the case of chip kill, this translates to requiring 8 out of the 9 chips to be operational. And in the case of IBM RAM, 4 of the 5 channels need to be operational for the system to function in an error-free manner. When we say channels here in the case of IBM RAM, essentially any component up to and including the channel, like the cells, chips, DIMMs, under the single channel can suffer an uncorrectable error and the system will still continue to function. In comparison, when by employing full replication, DWE creates a parallel N model system. The two subsystems in DWE are completely independent and parallel. Thus, it provides higher reliability. As you can see, there are more ways for the competitors to fail than DWE, and this is the intuition. Another notable point is that DWE protects memory holistically at the highest endpoint, that is, at the memory controller. And this resembles a top-down design approach, as opposed to chip kill and RAM, which aim to protect subcomponents in a more of a bottom-up design philosophy. Finally, it is worth noting that our analytical model does not account for other memory subsystem failures like those in address bus, data bus, memory controllers, etc., due to the absence of field data for these. However, unlike our competitors, DWE has the ability to recover from such failures as well. Hence, our analysis serves only as a lower bound of benefits for DWE. Next, let's examine how DWE provides memory performance gains. The insight that DWE brings here is to use the presence of this replica as the opportunity to improve performance. Let's see this in action in our running example. As shown in the figure here, in today's multi-chip NUMA architectures, a miss for cache line A in the LLC of socket 1 must traverse the intersocket interconnect, and this incurs high access latencies. However, in DWE's coherent replication technique, the request for cache line A is routed to the nearest replica, in this case, the socket 1's local memory replica. But DWE must also ensure safe access to the replica DRAM data. For example, if cache line A is held in dirty state in socket 2's on-chip caches, then access to the replica memory should not be permitted. This is to enforce the SWMR invariant of coherence, that is, single writer, multiple readers. For this, DWE introduces a replica directory, which holds metadata to permit memory access if and only if the replica data is up to date. DWE introduces this technique that we call coherent replication. It builds hierarchically on top of any existing cache coherence protocols. It maintains the replicas in sync as required for reliability and also provides coherent access to both of the replicas during the common case fault-free operation and thereby improves performance. DWE proposes two families of protocols to achieve coherent replication. They vary based on how replica access permissions are required. An allow-based protocol, which is a lazy or a pessimistic scheme, pulls permissions on an access. A deny-based protocol, which is an aggressive or optimistic scheme, pushes the deny permission. We evaluate the performance benefits of coherent replication using a simulator-driven methodology. We simulate a system with 2 sockets of 8 cores each using a trace-driven Gem5 simulator. The memory hierarchy has 2 levels of caches, a per-core private L1 cache and a socket-shared L2 cache, along with the 8 GB DDR4 memory per socket. We use a hierarchical coherence protocol with an intra-socket MOESI protocol and an inter-socket MOSI protocol. We use traces of OpenMP and pthreads based multi-threaded workloads from 7 different benchmark suites. We compare the performance of DWE against two configurations. A baseline NUMA system without memory replication. This is where requests are routed to the node where the data is housed. And a hypothetical Intel memory mirroring technique that actively load balances reads between its mirrored channels. The hypothetical Intel memory mirroring technique represents the best performance possible with today's state-of-the-art memory reliability techniques. This graph shows the performance of all of the configurations normalized to the baseline NUMA configuration without memory replication. The allow-based protocol provides a geomean speedup of 12% over all the benchmarks. And the deny-based protocol provides a geomean speedup of 15% over the baseline. A key point to note here is that all benchmarks for all schemes performs equal to or better than the baseline, which shows that the overheads of coherent replication does not cause any adverse performance penalty. 10 benchmarks show better performance with a deny-based protocol, while the other workloads show better performance with an allow-based protocol. This is attributed to the inter-socket sharing characteristic of the workload. Further details of this analysis are available in the paper. DWE also proposes to use a set dueling-like approach to profile and detect the best performing protocol. This dynamic protocol performs 18% better than the baseline over all the workloads. Lastly, compared to the Intel mirroring plus scheme, DWE's coherent replication technique allows avoiding inter-socket latencies by providing socket local reads. Thus, DWE provides a 13% better performance than the Intel mirroring scheme. Finally, we explain how DWE provides the reliability and performance benefit on demand. The need for on-demand reliability arises from the natural trade-off in DWE's replication scheme. That is, DWE inevitably incurs 2x capacity overhead to provide the reliability and performance benefit, as opposed to the 25% that is incurred by today's state-of-the-art DDR5 reliability schemes. The third insight that DWE brings to manage this capacity overheads issue is that we can opportunistically use the idle or underutilized memory capacity that is already provisioned in the system. Several recent works have reported this phenomena of a skewed memory utilization. That is, at least 50% of the memory is idle in 90% of the servers. This is because memory resources are often over-provisioned due to peak estimation. Secondly, DWE's overheads are applicable only as and when demanded by the application, unlike today's reliability schemes, which have fixed overheads at design time. For this, DWE provides an interface by which applications can allocate high reliability memory for only certain regions of their memory selectively. DWE provides this interface by using a hardware-software co-design approach, with the operating system working hand in hand with the hardware to enable or disable replication when desired. Thus, DWE provides a flexible trade-off between capacity and reliability. This allows deploying a large number of lower reliability or commodity DRAMs for capacity, while still being able to turn reliability on or off on demand. We now describe the operating system support needed to provide on-demand replication. The crux of the problem here is to provide a mapping between each physical address and its replica physical address. In DWE, this mapping is done at the page granularity. The replica page pairs are mapped by the OS. It creates pairs of pages in different sockets and stores them in a replica map table. This RMT is a single system-wide table that provides flexibility to create and destroy replica page pairs as needed. The hardware then walks this table at the directory controller, similar in spirit to the page table walker. The next aspect of this support is to answer how does the OS carve and manage the space required to house the replica pages. DWE uses the OS heuristics to estimate maximum DRAM resident set size. Once this is identified, the remainder unused DRAM space can be used for replication. If sufficient memory capacity is not available, then balloon drivers, similar to the ones used in hypervisors, can be used to steal memory. Page fault rates can then be monitored to ensure that replication does not cause excessive swapping. Note that disabling Dewey's replication allows falling back to baseline reliability that is provided by the underlying system. The last aspect of the support is to answer when should replication be enabled or disabled. We defer this decision to be managed as a soft setting by the control plane. That is, the server management and workload placement infrastructure make the enable or disable decision depending on the requirement of the workload. Again, several deployment options are possible here, including enabling Dway at per VM or per container granularity or in a kernel only setting. Dway's replication can also be explicitly specified by the application during the malloc call. Alternatively, Dway can be applied system-wide to replicate the entire memory address space. For this, a simple fixed function mapping can be used instead of the table-based mapping managed by the OS as discussed earlier. To summarize, Dway provides improved DRAM reliability over the state-of-the-art reliability techniques using replication. It improves performance using coherent replication in hardware. It accomplishes these goals with a flexible interface that can be deployed on demand. For more details and other auxiliary supporting material, like the simulator source code and the coherence protocol specifications, please visit our GitHub page and the website listed here. Thank you for your time.